Okay, activity 3 in chapter 9. It's really just our first activity, actually, but I guess it's labeled activity 3. So previous classes, we reviewed the definition of logarithms, both common logs with base 10 and any other base as well. Remember to rewrite it. We've got base, exponent, and answer, and just it goes back and forth. We can write it in either of those forms. We can take log form and write it in exponent form, and exponent form and write it in log form. We will be doing some solving now, being able to rewrite a given expression, whether originally in log or exponential. You could evaluate your expression and find the solution. However, you also found that it wasn't always as easy as you would hope. So we were asked to evaluate a log expression, log base 5 of 482. So there is a log base button on many of the graphing calculators. We're going to go through this activity just using the log key or the ln key. Some courses that you're going to encounter may only allow you to use a scientific calculator where there is not possibly a log base key. So we want to be able to solve these exponential equations with just using the log base 10 key or the ln natural log. So we'll talk about how we're going to do that. So the student proposed the following when they were given this expression, log base 5 of 482, set it equal to x. They rewrote it, 5 to the x equals 482. And then one way that we could solve that without having to even understand logs would be just to graph then. So we could put y1, 5 to the x, y sub 2, 482, and see where they cross. So they would cross at that ordered pair. So we'd have to set up a window so we could see that. And we would find out that the x value is approximately 3.3839. So that would be the exponent that would get me 482. So we could use our graphs, and you could have done that all the way back in advanced algebra as a step, or maybe even algebra 1. All right, but we want to be able to solve that, not necessarily just using the graph. So to solve that equation, they need to utilize a graphing feature of the calculator. Not all scientific calculators are going to have a graph feature, but all scientific calculators will have a log or a natural log key. The rest of the activity, we're going to review how we can evaluate logs and exponential expressions regardless of the base by using the log base 10 key in our calculator. Some things to remember, we're going to start here reviewing some of our exponent properties. So we've got 5 to the second times 5 to the fourth. And being able to simplify that, we would see that it's going to be 5 to the 6th. So we're going to add exponents when we're multiplying. So when we're multiplying, we're adding the exponents. Here I've got a division. I've got 10 to the 5th over 10 to the 7th. So that would be 5 tens being multiplied in the numerator and 7 tens multiplied in our denominator. So we'd be left with 2 of them in our denominator, which would be 1 over 10 squared, which would be the same as 10 to the negative second. A quick, easy way to get that, instead of writing that all out, would be just subtracting 5 minus 7. So we're going to subtract the exponents when we're dividing, subtracting exponents when we're dividing. And then here we've got 4 squared to the 5th. So that means 4 squared times 4 squared times 4 squared 5 times. So all together, if I go over and think about this rule, I would just be adding those exponents. So I'm going to end up with 4 to the 10th. I've got 10 fours that are being multiplied. So those rules are going to help us think about what's actually happening with our log properties. So the first one is called product property of exponents. So remembering what we did there, if I've got b to the a times b to the c, it's b to the a plus c. So we're going to add exponents. Keep the base and add the exponents. Quotient property, we're going to keep the base and subtract the exponents. And the power property, we are going to keep the base and multiply the exponents. B to the a to the c, b to the a times c. All right, since logarithms are nothing more than exponents, each of the exponent rules above can be rewritten using a log statement. So here we have one of the properties. Log base b of x times y equals log base b of x plus log base b of y. That is going back to this idea that we are adding exponents when we're multiplying two powers together. So that's what I have here. I'm multiplying x times y, and I can change it into the sum of two logs. So that might look a little far-fetched. So what we're going to do is, and what we did in this activity, if we were face-to-face, is we would have you guys each person pick a different value for x and y. So I picked 2 and 3 for x and y. So I punched in my calculator log 6, because that's 2 times 3. And then I typed in log 2 plus log 3, and those two answers were the same. So I understand, and you can plug in other values for x and y and see that indeed will hold. That pattern is going to work for any x and y that I pick. So whatever I get for the product there, put it in and then add. All right, so to put that together with some uses, that's that equivalent to the product property of exponents that we had up here, where we are going to add the exponent. So we'll go either direction. I have 2 different logs being added. They've got the same base. So if they have the same base and they're being added, I can put them together as a single log by multiplying the 2x and the 3. Very common mistake is students think they should be adding. That is not what happens here with logarithms. So logarithms, when I put these together, I put together the sum, I multiply those 2 arguments to get 2x times 3. That's what we just have shown up here. This one, natural log of x squared plus natural log of x to the third. So again, I'm adding 2 logs with the same base, so I can put them together as a single log by multiplying the 2 arguments together. And then I can actually go ahead and use one of my other properties and rewrite it as natural log of x to the 5th. The third one has us go the other direction. It says write as 2 separate logarithms. So now I have natural log of a product. So I can separate it up into natural log of e to the third plus natural log of e to the 11/12. So we separate it up. It's just like we did up on that one in red. All right, so to summarize that, when the argument of the logarithm is a product, the expression can be rewritten by separating into 2 logs and adding them. So that's what we did right there. Separate it into 2 logs and add them together. All right, so that's one of our properties. Another one of our properties is this: log x divided by y equals log x minus log y. This comes from the idea that we subtract exponents when we're dividing. When we divide, we subtract exponents. Log just means exponents. So again, if we were face-to-face, we'd have you guys all kind of pick different numbers and see if it worked. So I picked 3 for x and 4 for y, and I typed in log 3/4 or log 0.75, and then I typed in log 3 minus log 4, and I got the exact same answer as when I did log 3/4. And you can test it with an x and y that you pick, and you'll see that indeed that's also going to work for yours. All right, so then we'll do a couple of examples like we did before, but now we're subtracting logs. So I'm going to take the argument and I'm going to divide them. 2x divided by 3x, and we can simplify that. X over x would simplify to 1, so we would get log of 2/3. Natural log x squared minus natural log of x to the third. So put it together, natural log of x squared over x to the third, and that can simplify. I'd end up with that should be a natural log 1 over x. So it simplifies. And then we go the other direction. Natural log of e to the third divided by e to the 11/12. So then we can subtract natural log e to the third minus natural log e to the 11/12. Now, when you subtract, the order does matter. So make sure you recognize that it's the log of the numerator minus the log of the denominator. And that's what we did here. If you realize I was subtracting the 3x, the log 3x, so the 3x is what goes on the bottom. I was subtracting the natural log of x to the third, so the x to the third is the part that goes on the bottom. So to summarize that, we can separate into 2 logs and subtract them. It's the log of the numerator minus the log of the denominator. All right, and then our third log statement is log of x to the p equals p times log of x. So for that one, again, the idea is I can take that p power exponent and bring it down in front as a multiplier. So we will use that quite a bit when we're trying to solve when our variable is in the exponent. So I picked some numbers again. You could pick your own. I did log of 3 to the second. So I typed in log of 9. And then I typed in 2 times log of 3, and I ended up with the same answer. So that seems to work. We could try it with different numbers and give us a pretty strong sense that indeed that property is going to hold. So let's try it a few times just like we did before. Log x squared, I can take the 2, bring it down in front as a multiplier, 2 times log x. Natural log 2x in parentheses squared, so both of these things are being squared, so I can bring the 2 down in front, 2 times log 2x. Notice on part 3, that's a little bit different. The difference there is that there aren't parentheses. It's natural log of 2x squared. So this one, I'm going to have to use 2 properties, because if I just brought the 2 down in front and made it look like this, it would make us assume that the 2 was also an exponent on this 2. But it's not. It's only on the x. The exponent on 2 is 1. So the first thing is I'm going to go back and use the first property that we talked about back in number 3. And that's where I have to think of this as a product, 2 times x squared. So then I break it apart. I've got a product, so I break it apart into log 2 plus log x squared. Those are the two things being multiplied. And then I can bring this 2 down in front of this log and keep the log 2. So log 2 plus 2 log x. This is now indicating the exponent on 2 was just 1. There's just a 1 out in front here. And the exponent on the x was a 2. And I said there, notice the exponent is only on the x. So when the argument of the logarithm is raised to another exponent, the expression can be rewritten by bringing the exponent in front as a multiplier. So when I have a power of a power, a logarithm is raised to another exponent, power to a power. What do? We multiply. So again, it kind of goes back to those exponent rules that we had before. All right, so how can we use those? So here I have a few examples. Log base 13, I'm given these decimals. Log base 13 of 6 is that decimal. Log base 13 of 3 is that decimal. And I'm supposed to be able to evaluate these log base 13 of things that are not 6 and not 3. So log base 13 of 2. Well, I know it's going to be less than that number, but how can I get there? Well, the idea is, can I rewrite 2 using 6 and 3? And I would like to use either an exponent or division or multiplication. Well, I think 6 divided by 3 is going to be 2. So this log base 13 of 2 is the exact same as log base 13 of 6 over 3, because 6 over 3 is 2. And then I can rewrite, when I have log of a quotient, 2 things being divided, we're going to subtract the individual logs. You subtract exponents when you divide. That's where that comes from. All right, so this, I know there's a decimal for it. It's right there. This, log base 13 of 3, there's a decimal for that. So ignore what's on the right for right now. We're just looking at the left-hand side. I'd have those 2 decimals, and that would be my answer. So log base 13 of 2 must be that decimal approximation. We'll go to B. B I've got in the middle here. So log base 13 of 18. So 18, how can I get 18 from a 6 and a 3? I could multiply. So 6 times 3, log base 13, 6 times 3, that's the same as 18. And now that I have multiplication going on here, I can split it up into 2 separate logs, and I'm going to add them. I've got those 2 decimals. Log base 13 of 6 is 0.6986. Log base 13 of 3 is 0.4283. And we're going to add, and I end up with 1.1269. And the last one over here, we gave a hint, 1,458 is the same as 6 times 3 to the 5th. So I just replaced 1458 with 6 times 3 to the 5th. This one, I'm going to use 2 of the properties. I have a product and I have an exponent. So I split it apart. I would have had 3 to the 5th here. I kind of did it in one step. I can bring the 5 down in front as a multiplier there. So I have the decimal for log base 13 of 6. I have the decimal for log base 13 of 3, and I multiply that by 5. So 0.6986 plus 5 times 0.4283, and we end up with 2.8401. So that's how we can use some of the properties to do some rewriting, even when these numbers are not 6 and numbers are not 3. Find a way to rewrite it. All right, so how else can we use this to help with solving? One of the primary uses of logarithms is to help solve exponential equations. The primary property we will be using is the power property of logarithms. So study how Nemo evaluates the log statement with the base other than 10 or e that we could just plug in our calculator. So log base 5 of 482. This goes back to that question before. So he takes that log expression, sets it equal to x, and then rewrites it into exponent form. So base is 5, exponent is x, answer is 482. And that's the question, is what is the exponent that's going to make 482? So step 3, takes the log of both sides. Equal, balanced move, that's an okay thing to do. By doing that, it then allows us to use our property like I had up here, where I had the 5 as the exponent on the 3 and brought it down in front as a multiplier. Well, now the exponent's x. So I can bring the x down in front as a multiplier. I don't know how to undo an x exponent. There's no x root or anything that's going to help me there. But I do know how to undo multiplication. So that's what we're going to try to get to. So x times log 5 equals log 482. I'm going to divide by log 5, because remember, that's just a decimal. It's programmed in the calculator. We can definitely multiply or divide or do anything that we want with that particular decimal. So we divide here and divide over here. This simplifies out to just be x. This, when I type it in, I have to type in the whole thing. Do not make that mistake. I've seen students make that mistake before where they just divide the numbers. We need to have log 482 divided by log 5. Make sure you use parentheses appropriately as well, and you can get 3.839. So try that. If you have to, pause the video, make sure that you plug that in and see that you get that decimal when you do it. All right, so just picking apart the thinking. What did he do? Explain the balanced move that he made in step 3. So he took the log of both sides of the equation. What base did he use? I don't see a base there, so that must be base 10. Why did he use base 10 instead of keeping it as base 5? Because log base 10, there's a button on any scientific calculator that's going to be log base 10. So that just the LOG button. So we use that one because it's easy to use, easy to find, and it'll help us in our solving. And then why was he able to bring down the exponent in step 4? Well, that's the power property of logs that allows that simplification. So we can bring the x down in front as a multiplier, and then we know how to undo multiplication. All right, so let's look at a couple of examples. One little twist. What if I started off with this? We've got Fern, who needed to solve this exponential equation. Thought the best step would be to log both sides right away. Hey, if she does this, she actually is not allowed to use the power property of logarithms to bring down the x. So in other words, why can't I take this x and bring it down in front? It's an exponent. We said before we can bring it down in front. But think about what's happening. Is the x the exponent on the 20 or the 3 or the 20 and the 3? It's only on the x. So when I bring it down in front, it makes us believe or think that the x was actually outside here and it was the exponent on both of those things. It's not. The exponent of x is not applied to the 20. It's only on the 3. All right, so knowing that, let's see what we maybe should do as a first step instead. Knowing that Fern's first step is incorrect, solve this equation for Fern, show all work. Remember to use order of operations, log functions are grouping symbols. So we have to take care of the log part before we can do anything else that's there. All right, so I actually went back to this statement and I separated it. So I separated this by using the product property where I can turn it into the sum of logs. And then I brought the x down just in front of the log 3. All right, so going from here, using the correct steps, this would be the first thing. separate it, and then bring the x down. Then I could subtract this from both sides. Again, I'm trying to solve for x, so I want to get the log 20 to the other side. Then remember, these are just decimals, so I can type in log 2 minus log 20, and we get a -1. You could actually use one of your log properties here, and you could get 2 divided by 20. So log of 2 divided by 20 would be log of 1 over 10. And 1 over 10, log of 1 over 10 would be thinking 10 to the what is 1/10, and 10 to the -1 is 1/10. So you could actually get there without a calculator for that particular step, or just punch it in and you'll see that it is -1. And then finally, I need to finish solving for x, so I need to undo this multiplication. So I'm going to divide by log of 3. So x equals -1 divided by log 3. Type that in the calculator, and we get -2.0959. All right, so there could be other steps that you could do first. If I wanted to, I could have divided by 20 first. Like if I were starting with this problem way up on top, that's probably what I would have done first. I just would have divided by 20 and then taken the log of both sides, so I wouldn't have to worry about that 20 inside with the 3x with the log. But we'll have some of those that we're going to practice too coming up here. All right, bottom half of that page, number 9, part A, looking at the first one, log base 8 of 5,000. So using the steps from Nemo, the first thing I'm going to do is I'm going to rewrite it in exponent form. So again, just ignore what's on the right there. Exponent form, 8 to the x equals 5,000. Now I have my variables in the exponent. So to fix that, we're going to log both sides to get the x out of the exponent. So I take the log of both sides. That allows me to bring the x down in front as a multiplier. So now I have x times log 8 equals log 5,000. And then I need to get rid of the log 8, so I'm going to divide by log 8. So log 5,000 divided by log 8. And then I pick up the calculator. In the log button, base 10, that's right there on your calculator. So type it in, use parentheses like we're supposed to, and we end up with that decimal. Part B, and I've already shown you here, I've got this 3.21 to the x plus 13 equals 15. So the first thing I'm going to do is I have to get this, what has the exponent on it, by itself. Just like over here, I would have divided by 20 first if I would have started with this. So here, the first step is subtract 13. So I get a 2. And I just rewrite it. I put the x on the left side, the 2 on the right side. So it kind of matches up with what we're going to have over here. All right, x is in the exponent. I need to log both sides, bring the x down in front as a multiplier, and then divide by log 3.21. Punch it in, get my decimal. So you'll notice the steps, once I get to here, would be the exact same steps as I had over here. Different numbers, of course, but same steps. So if I can get it rewritten this way, I'm pretty well set as far as what I should be doing. Hopefully we're good with those steps. All right, next one, 5 times x to the third equals 100. All right, so this one, I'm going to divide by 5, and then I get x to the third equals 20. Common mistake, students get into is, oh, I've got exponents, so they think I need to log. You only need to log when the variable is in the exponent. So this one, it's x to the third. We just solved a bunch of these on our last 2 days, and even on that little check-in quiz. So we're going to take the cube root. That's how we get rid of a third power. So we cube root 20, and whatever that decimal is, I just left it exact. So it's the x equals the cube root of 20. I think it's about 2.7144 if I type it in here quickly. Part D, this one is just like the one that Fern had to do. So instead of logging right away, let's get what has the exponent by itself. So my first step here would be divide by 5. So notice these are pretty close. All we did is switch the x and the 3. Now it's 3 to the x as opposed to x to the third. This one I'll need logs. So first step, divide by 5. 3 to the x equals 20. Take the log of both sides, bring the x down as a multiplier, and then divide by log 3. So there's our exponent, 2.7268. These are really easy to check. Type in your calculator, 5 times 3 to the 2.7268, and hopefully we get something really close to 100. Really easy to check those. All right, so an application. Insulin breaks down at a rate of 5% every minute once it has entered your bloodstream. We have the following equation to model this situation. 10 times 0.95 to the x. X is the time since insulin was injected in minutes, and y is the amount of insulin remaining in the bloodstream. All right, so let's make sure we understand that equation. What does the value of 10 represent? Well, 10 is the initial amount. This is our kind of generic exponential y equals a times b to the x. So 10 is the initial amount. Well, why is it 0.95 to the x? There's no 0.95 in this sentence. Well, remember, if it's breaking down at 5%, 95% is going to remain. So the 0.95 is the amount that remains in the bloodstream each minute. Determine how long it takes there to be 2 units of insulin remaining in the bloodstream. So maybe in whatever this is, maybe this is a different type of drug, but maybe the patient has to have at least 2 units in their bloodstream. So they want to know how long does it take for that to happen. So they have to have another dose, or they have to have something else happening. So we set up 2 equals. 2 is the amount that's remaining. So that's the y. So now we have 2 equals 10 times 0.95 to the x. This looks pretty similar to that last one that we just solved, different numbers, but same setup. First step is going to be divide by 10. So I get 0.2 equals 0.95 to the x. Now I have what has the exponent by itself. So I'm going to log both sides. Bring the x down. I put this over on the left-hand side to make it kind of mirror what we did before. And then I'm going to divide by log 0.95. So log 0.2 divided by log 0.95. And then the decimal for that would be about 31.4 minutes. Next one says determine the half-life. So half-life, remember that means how long does it take for half of the substance to remain. So if I started with 10, I really want to know how much time does it take for there not to be 2 this time, but how much time does it take for there to be 5 units. So I put 5 in for y, and I'm going to solve the exact same way. So this one, obviously, it's going to be less time than before. If you got something bigger, we know we did something wrong. But same steps, divide by 10, take the log, bring the x down, and then divide. So again, you can try that. Make sure that you can enter that into your calculator, and we should hopefully be fantastic with that. All right, explain why you cannot always use the log key on your calculator to evaluate a log expression. Well, the log key, log, is always base 10. And if you're asked a question that's not base 10, you can't use that unless you do the solving like we were doing on these and on the previous one. So I can't type in this, for example, log base 8 of 5,000. If I type in log 5,000, that doesn't mean base 8. That means base 10. So I want to make sure that I understand that that log button is always base 10. So have to make sure I realize that. How would I solve? Now we have this general, a times b to the x equals c. So that's like this one here, like the one that we did previously on the other page. So we're going to divide by a, we're going to log both sides, we're going to bring the x down, and then we're going to divide. And there are the steps. And would I have to use log base 10? No, I could use log base e if I wanted. I could use the ln button because that's going to show up on every one of your scientific calculators as well. It doesn't matter because both can be found on the calculator. Sometimes it's actually to your advantage to use that natural log when the e is involved in the situation, which it will be in many times when there's a continuous growth or a continuous formula. You will actually have an e in the equation. When I see an e in the equation, the variables in the exponent, I will use the natural log on both sides to help me do the solving because it makes it a little bit easier, a little bit more that I can do without having to use the calculator for that one. All right, so there's activity 3. So hopefully we're set to use those properties and be able to simplify and be able to complete that work.